Okay, so here we are. The last class, we finished off on this slide here where we talked about Zaitsev's rule. And time permitting this evening, we're going to look at some problems that deal with Zaitsev's rule. But I wanted to start by talking about the oxidation of alcohols, namely the oxidation of primary alcohols. If we take a primary alcohol, and how do we know that this is a primary alcohol right here? We know it because the carbonyl carbon, which is this carbon I'm circling in red, is attached to only one R group. Right? If my carbonyl carbon was attached to two R groups, it would be a secondary alcohol. And if it was attached to three R groups, it would be classified as a tertiary alcohol. So specifically, when you take a primary alcohol and you oxidize it. Now, the symbol that we use to represent oxidation in organic chemistry is the O in these square brackets. That represents an oxidizing agent. Now, you might be wondering what kind of agents or reagents are used as oxidizing agents. And the answer is we have a couple of possibilities. You can either use potassium permanganate and hydroxide, or you can use H2CrO4. And H2CrO4, this is called chromic acid. Now, you might be wondering, why are you showing me two different ways to oxidize a primary alcohol, Mr. Dion? The reason why is because chromic acid is an acid, and potassium permanganate and hydroxide is a base, right? It's a basic reagent because hydroxide is a base. So depending on whether you want to do the reaction in acid or in base, you've got a couple of possibilities. Now, what happens here when you oxidize a primary alcohol is that you end up losing water in the first step. So where are we going to get water from? We're going to get it from H2, and the oxygen is going to come from our oxidizing agent. Once all that water has been taken out, we're going to form a double bond between the oxygen and the carbon, and that's this one here. So we end up with an aldehyde. Something that's not shown on this slide is that you can further oxidize an aldehyde. What do you mean, Mr. Dion? What I mean is that you can oxidize an aldehyde even more. You can oxidize an aldehyde all the way to a carboxylic acid. And that would just take a second equivalent or a second molar equivalent of the oxidizing agent, and it will actually put an oxygen in between this carbon and hydrogen to make a carboxylic acid. So if you're asking, well, what's the answer? When I oxidize a primary alcohol, do I get an aldehyde or do I get a carboxylic acid? If you treat it with a really strong oxidizing agent, it's going to go all the way to the carboxylic acid. And if you treat it with something that's more mild, it's going to stop at the aldehyde. And we'll try to look at some examples of that. If I have a primary alcohol, here we go. Here's a perfect example. I have this alcohol, 2,2-dimethylpropanol. Where does that name come from? We find the longest carbon chain. We give the hydroxyl the lowest possible number. So we have 1, 2, 3. So we have a methyl here. We have a methyl here. So it's 2,2-dimethyl. We have 3 carbon chains. And our alcohol is here. So we have 2,2-dimethylpropanol. Okay, like that. And now we're going to treat that with our oxidizing agent. What are we going to do? We're going to remove H2, and our oxygen is going to come from our oxidizing agent. And that is what's going to form the water molecule. What's going to be left over is that we're going to form a double bond between the carbon and the oxygen. That's this one here to form the aldehyde. Again, this could be further oxidized. Again, this is if you treat it with a really strong oxidizing agent to give you, and I'm just going to draw the bond line structure, to give you this compound where you would produce a carboxylic acid by inserting an oxygen in between this carbon and this hydrogen. So the take-home message is that when you take a primary alcohol, and you treat it with an oxidizing agent, you get an aldehyde, and I'm kind of running out of space here, but an aldehyde can be further oxidized to a carboxylic acid. I promise that the oxidation of a secondary alcohol isn't quite as complex. Let me show you. If you have a secondary alcohol, how do I know this is a secondary alcohol? Because my carbonyl carbon has 1, 2 R groups attached. You can simply memorize that whenever you have a secondary alcohol, and there's no exceptions, when you oxidize a secondary alcohol, you're going to end up producing a ketone. How do we produce a ketone? Well, we're going to do our reaction with our oxidizing agent, and we're going to produce H2O. What do we need to make H2O? We need 2 hydrogens and the oxygen from the oxidizing agent to make our water molecule. Then we're going to still have our 2 R groups attached to our carbon, but now we're going to form a double bond, and that's this bond here, and that is how you make the ketone. Okay, so not only are we oxidizing, we're producing a ketone, we're also eliminating the 2 hydrogens that I have circled in red, this one and this one. Okay, oxidation of a secondary alcohol. One of the easiest reactions that you'll have to memorize in this class is a tertiary alcohol oxidation, because it doesn't exist. If you take a tertiary alcohol, any tertiary alcohol, there are no exceptions to this rule, and you try to oxidize it, what you get is no reaction. Organic chemists usually abbreviate that as N/R. It just means no reaction. Nothing happened. The reason why, and I can write it here for you, no exceptions to this. Okay? So if I ask this on your next exam, you just say nothing happens, man. If you take a tertiary alcohol and you try to oxidize it, you get nothing. And the reason why there's no reaction is because there is no hydrogen on the carbonyl carbon to remove. Okay, and that shouldn't say the carbonyl carbon. That's a typo. It should say the carbonyl carbon. So in other words, there is no hydrogen attached to this carbon. All you have are R groups. If we back up in our slides, we go back to the secondary alcohol. See, there's a hydrogen attached to the carbon, and if you go back to the primary, there's actually 2 hydrogens attached to the carbon. So in order for an oxidation of an alcohol to occur, it's got to be either primary or secondary. And the reason why it works for the primary or secondary is because they both have at least 1 hydrogen attached to the carbonyl carbon. When you've got a tertiary alcohol, you have no reaction. Nothing at all happens. Section 12.5 deals with oxidation and reduction in living systems. So this is a little introduction to some biochemistry. The bottom line is that I'm not going to ask you a ton about this. I might ask it one question. And the reason why is because we're going to look at so many different oxidation and reduction reactions once we get into the later chapters, like chapters 19, 21, and 22. You might remember from Chemistry 101 this definition of oxidation and reduction. This is what we call oil rig, right? And the oxidation stands for, or the oil rather stands for oxidation. Oxidation is losing electrons. So oxidation is the loss of electrons. Rig stands for reduction. Reduction is gaining electrons. So oxidation is losing electrons and reduction is gaining electrons. Now, if you studied Chemistry 101 at PPCC, I know you would have seen this concept come up for sure in your class. And I'm sure you all mastered the content. However, what you looked at in Chemistry 101 would have been inorganic systems. And then you see cations and anions, and it's pretty easy to figure out how many electrons are being lost and gained. But in organic systems, which is what we're concerned with in this class, it's actually sometimes very difficult to determine whether oxidation or reduction has taken place because we don't see charges, right? If you think about all these organic molecules that we look at, we seldom see charges. And so how would we know whether oxidation or reduction is occurring with an organic molecule? And we have a very simple couple of rules that we use to determine when oxidation or reduction are occurring in an organic system. Here are the rules. When we have oxidation results from either the gain of oxygen or the loss of hydrogen. One of those. If you think about what oxidation is, right, adding oxygen, well, it makes sense that if you gain oxygen, you're undergoing oxidation. It might not be as intuitive, but when you lose hydrogen, that's also considered oxidation. Conversely, when we talk about reduction can be the loss of oxygen or the gain of hydrogen. You need to memorize these rules. Okay? You need to commit these to memory because they're going to come up so often in this class. If we look at the chart or the figure at the bottom, we go from an alcohol to an aldehyde to a carboxylic acid. Notice that the arrow is pointing towards the more oxidized form. So what it's saying is that when you go from an alcohol to an aldehyde to a carboxylic acid, you're getting more and more oxidized. Namely, the carbon is becoming more and more oxidized. Let me prove it to you. If you look at the carbon that I have highlighted in the alcohol, you can see it's got 2 hydrogens and 1 oxygen attached to it. When we go over to the aldehyde, not only do we lose a hydrogen, right here we have 1, 2, 3. We've only got 1 here, so we lost 2 hydrogens. You could write that down, loss of 2 hydrogens. But you also gain an oxygen. If you're saying, well, look, there's only 1 oxygen here and 1 oxygen here, what do you mean? You're gaining a bond to oxygen. Here you only have 1 bond to oxygen, but here in the aldehyde we have 2 bonds to oxygen. So we'll put here gain oxygen. Even though it's just a bond, we consider that gaining oxygen. And then when we move over to the carboxylic acid, there's no change in the number of hydrogens. We had 1 hydrogen here. We've still got 1 hydrogen here. But what did we do? We gained 1 oxygen atom, right? This one here is brand new. So that's what more oxidized means. Now, if you're really astute and you're asking me, well, hold on, Mr. Dion, what if I go backwards from the carboxylic acid to the aldehyde to the alcohol? Would that be becoming more reduced? And the answer is absolutely. Absolutely it would be. All right. Here's an example of a biological oxidation reduction reaction. By the way, oftentimes in chemistry, you refer to oxidation reduction reactions as redox reactions. So redox, you've probably seen that in your chemistry 101. NAD plus is an acronym for nicotinamide adenine dinucleotide, and it's a coenzyme that's commonly involved in a lot of different biological oxidation reduction reactions. Now, if we look at this organic molecule right here, this is called malate. It's the conjugate base of malic acid, which I think is the acid responsible for the tart flavor in Granny Smith apples. Anyhow, we have this molecule right here. You can see that there's an alcohol in it, right? There's an alcohol right here. What happens is when you treat it with NAD+, which is your coenzyme, and malate dehydrogenase, so this is your coenzyme, and this is your enzyme, okay? You end up forming this molecule. You go from malate to oxaloacetate. What's happening when we go from the malate to the oxaloacetate? That would be considered an oxidation. Why? Because when we go from here to here, we're losing these 2 hydrogens, so loss of 2 hydrogens, and we're gaining a bond to oxygen. So gain of oxygen. Well, something else you probably remember from Chemistry 101 is that you can't have oxidation without reduction. They have to occur simultaneously. You can't have any reduction without oxidation, and you can't have oxidation without reduction. Well, the question then becomes, if my malate is being oxidized to oxaloacetate, right? So this is oxidation. What's being reduced? Well, if you look at the NAD+, it's going from NAD+ to NADH, and the H stands for a hydrogen. So this is gain of hydrogen, and therefore this is a reduction, right? You can't have one without the other. There we go. So that's something that we're going to see later on in the class, but I want you to understand what's going on here, that the malate is being oxidized to oxaloacetate, and that the NAD+ is being reduced to NADH. Well, let's switch over to section 12.6, which deals with phenol. This is a ball and stick model of phenol right here. If we just draw the bond line structure of phenol, if I draw this, C6H6, you will all recognize that as benzene. If I add an alcohol or a hydroxyl on here, then I have phenol. Okay, phenol. Now, what about phenol? It says phenols are compounds in which a hydroxyl group, that's this, is attached to a benzene ring here. They're polar compounds because of the hydroxyl group. Right now, I've drawn it partially condensed here, but if you look at the hydroxyl shown right here, you have your oxygen, hydrogen, you have carbon, 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 carbon. And you have all these hydrogens here, which I'll put in. Okay, we know that there are some dipoles here. There's a dipole between the carbon and the oxygen because oxygen is more electronegative than the carbon. And there's also a dipole between the hydrogen and the oxygen because oxygen is more electronegative than hydrogen. Again, oxygen is the second most electronegative element in the whole periodic table. There's only one element that's more electronegative, and that's fluorine. And so if you add these two vectors together, the resultant vector is going to be in this kind of direction. And so that is why you can see that phenol is a polar compound. If we have simple phenols, and you might be wondering what's a complex phenol, we'll look at some other phenol derivatives in a second, but simple phenols are somewhat water soluble, and they have a variety of uses, including contributing to the to different flavorings and odors. Now, in order to have a phenol, the hydroxyl has to be attached to an aromatic ring. This is a mistake that I'll see students make from time to time. I'll just draw it here. If I just draw a six-membered ring like this is cyclohexane. If I put a hydroxyl on it, this is cyclohexanol. Look at this last class. Cyclohexanol is not a phenol, right? Cyclohexane and benzene are two very different molecules. Some phenol derivatives. Phenol derivatives have many uses. Now, if you're wondering what's a derivative, it just means a compound that is closely related to, kind of looks like it, okay? A relative almost, if you will. If you look at, here's phenol. It's got some interesting names. A really old name is it's called carbolic acid. It's when they dissolve it in water, and I think it's used as an antiseptic. I think they used to use it as an antiseptic in barbershops when they put the combs in it and stuff. They put the combs in carbolic acid, which was just a solution of phenol and water. Then you have these other ones over here, okay, that are antiseptics. You can see they're used as, germicides, as disinfectants. They all have phenol in them, right? If I circle, here's phenol in this molecule here. There's another phenol over here, right? If I look here, you can see kind of two phenols, right? There's one here, and then there's a hydroxyl there. But either way, and then there's a phenol here. So these are what we call phenol derivatives. They're phenol with other things tacked onto them, okay? The only one that you have to memorize for our class is plain old phenol. You don't have to memorize these other three on the right-hand side of the slide. Just know that phenol derivatives are used as antiseptics. Let's move on to section 12.7, which deals with...
I'm sorry, Mr. Dion, which one did you say that we had to memorize?
You have to memorize phenol itself.
Oh, okay, none of the derivatives?
No, you don't have to memorize any of the derivatives.
Okay, thank you.
You don't have to memorize any of those three compounds there. All right, just this one. No. Now, I'm not saying that's the only compound you need to know in this class, but on this slide, it's the only one you need to know. All right, let's move on and let's talk about ethers. Ethers we looked at way back at the beginning of the class because we started our discussion really early about functional groups. And we said when we have an oxygen between two R groups, whether they're the same or whether they're different, it didn't matter. We called that an ether. And we even did some practice in class where we identified functional groups. Now it says here that the R group can be aliphatic or aromatic. If you're wondering what the heck is aliphatic, aliphatic is anything that's not aromatic, okay? Anything that's not a benzene ring. Now it says here that ethers are slightly polar due to the carbon-oxygen bond. They do not hydrogen bond with one another because there are no oxygen-hydrogen bonds, right? We know that for hydrogen bonding, you have to either have a bond between hydrogen and oxygen, hydrogen and nitrogen, or hydrogen and fluorine. These are what are needed for hydrogen bonding. If I just draw the ether that's shown down here, this is dimethyl ether. I'll write it like this. Okay, I have a bond to the oxygen, another bond to the oxygen, and I also have two lone pairs. Think about water. You know that water has a bent geometry. Oxygen has 2 bonds and 2 lone pairs. The same thing for an ether. So we know there is a difference in electronegativity between carbon and oxygen. Carbon has an electronegativity value of around 2.5, and oxygen has an electronegativity value of around 3.5. That means that the difference in electronegativity is 3.5 minus 2.5, which is 1.0. That falls in the range of a polar covalent bond. So that means between this carbon and an oxygen, I can draw a dipole going this way. And between this carbon and oxygen, I can draw a dipole going that way. The resultant vector, when you add those two vectors together, is that you end up with something like this. So you do end up with a functional group that is polar. However, it says that it's only slightly polar. And the reason why it's slightly polar compared to something like water, which is highly polar, right? And we could draw the dipoles in for water. Water is highly polar. And the reason why is because of these methyl groups, right? The R groups that kind of block the dipoles a little bit. It makes it more difficult for them to interact, the ethers to interact with other molecules, okay? So that's why they're not quite as polar. Well, if we look at the physical properties of ethers, what you'll see is that ethers have boiling points that are somewhere in between those of analogous alcohols and alkanes. So if we look at the 3 compounds that are on this slide, you need to be able to do this. Okay, what I'm going to do right now, you need to be able to look at these 3 compounds and be able to determine which one's going to have the highest boiling point and which one would have the lowest boiling point. You see that all 3 of these compounds have a very similar molar mass, all in the neighborhood of 58 to 60 grams per mole. But if you look at their boiling points, they're very different. We go from minus 0.5 for butane, all the way up to 8 for the ether, and then all the way up to almost 100 for 1-propanol. Why would that be? It's based off of intermolecular forces. So you have to be able to explain boiling point trend based on intermolecular forces, which is a concept that you would have learned in Chemistry 101. If I look at a butane molecule, okay, here I have butane. Who could tell me what intermolecular forces are found in between 2 butane molecules, 2 or more? Exactly. Thanks, Gavin. The answer is London forces. That's the only intermolecular forces that are experienced between hydrocarbons, right? We went over that a lot in chapters 10 and 11. Because in a hydrocarbon like butane, there are only carbon-carbon and carbon-hydrogen bonds, both of which are nonpolar, and so there are only London forces. Whereas when I have an ether, I have that carbon-oxygen-carbon bond, and we went over this in the last slide, and we said that ethers are slightly polar. Well, if they're slightly polar, that means they have a dipole. So what would be the major intermolecular forces that an ether would experience, like ethyl-methyl ether? Anyone? What would be the major intermolecular forces experienced between molecules that have dipoles? It would be dipole forces. Thanks. Thanks, Sunmi. All right. And then lastly, we have 1-propanol, which has a hydroxyl, and so it is capable of hydrogen bonding. Okay. Now, when it comes to intermolecular forces, we know that the strength increases as we go from London forces to dipole forces to hydrogen bonding, right? These are the strongest, these are the weakest. And so that explains why propanol or 1-propanol has a higher boiling point than the ether, and the ether has a higher boiling point than the alkane, butane. Before we move on, I just want to point out one more thing, okay? Just because an ether is polar doesn't mean the only intermolecular forces it experiences are dipole-dipole forces. Every molecule under the sun experiences some London forces. Okay? The reason we're more concerned about the dipole-dipole forces is because they're stronger. Okay? But the London forces are still present. Doesn't mean they don't exist. The same thing with the alcohol. Even though it has hydrogen bonding, which is the strongest of all the intermolecular forces, alcohols are polar, and so an alcohol also experiences dipole forces, and it also experiences London forces. Now, if you're wondering again, why don't you talk about those ones, Mr. Dion? Because we are concerned with the strongest ones. That's the ones that we use to explain the boiling point trends, the strongest intermolecular forces present in a molecule. All right, let's talk about some ether nomenclature. There's some really interesting ether nomenclature, especially when it comes to common names. Common names for ethers consist of the names of the two groups attached to the oxygen listed in two different possible orders. You can either go by alphabetical order or by size, and then you follow it up with the word ether. Let's take a look at some examples. If you look at the first one, we have two methyl groups attached to our oxygen. So that would be dimethyl, and there's no alphabetization to worry about. And there's no size difference, right? They're both identical. So you'd call that dimethyl ether. And a third, or another rule that's not on here, is whenever you have two groups that are the same, like a dimethyl, you can actually scratch off the di and just call it ethyl ether, or sorry, methyl ether. The same thing would apply for diethyl ether. So if you had, I'll just add an extra example here since it slipped out of my mouth. If you had an ethyl group and an oxygen and another ethyl group like this, okay, that would be called diethyl ether. But if you just said ethyl ether, everybody would know what you mean. Okay, either one is acceptable in that case. When we move on to unsymmetrical ethers, so where we have two different R groups, then it gets, again, more interesting. We have to apply one of these rules. On this side, we have a methyl. On this side, we have an ethyl. If we name it according to alphabetical order, E comes before M, so we'd call it ethyl methyl ether, right? That would be the alphabetical way of doing it. If we do it according to size, the size goes from small R group to large R group. Here you have a methyl, here you have an ethyl. Ethyl is bigger than methyl. So according to size, you would call it methyl ethyl ether. So either one of these is acceptable. And then in the last example, we have an ethyl group and an isopropyl. It doesn't matter if you name it according to alphabetical order, E comes before I, or if you name it according to size, an ethyl group is smaller than an isopropyl group. Either way, you only end up with one common name, and that is ethyl isopropyl ether. That's it. So those are common names. Again, and I've said this to you many times in class, but in case you ever get frustrated in organic chemistry with common names, the reason that we have to learn them, even in an introductory class like this, is because they are so prevalent, okay? It's very rare that people would use systematic names for simple ethers. Now, systematic names, those are what we call IUPAC names. IUPAC is the International Union of Pure and Applied Chemistry. Systematic is another way of saying that, though. For the IUPAC nomenclature of ethers, what we do is something you're used to doing now. We find the longest chain, okay? We take the alkane name of the longest chain, and then the shorter chain is going to be named as an alkoxy substituent. What's an alkoxy substituent? Well, if you have, and I'm just going to break up on here, if you have OCH3, that would be called a meth, right? This would be a methyl, so this is called a methoxy. If you have an ethyl group in an oxygen, that's called an ethoxy. You can probably see where I'm going with this. If you have an O, CH2, CH2, CH3, that would be called a propoxy. Same thing applies for an isopropyl group. I'm kind of running out of space here, but if you had an oxygen, then a CH and two CH3s, this would be called isopropoxy. Anyhow, there's a whole bunch of them. Well, let's take a look at this example down here and see where this name comes from. 1-methoxypentane. The first rule was to find the longest chain. The longest chain is this one right here. We have 5 carbons in a row. The shorter chain is named as an alkoxy substituent. So we're going to take the chain and the oxygen along like this. You can see that that is an OCH3. We call that a methoxy. The methoxy is a substituent, and so we want to give it the lowest possible number. So we're going to start numbering at this carbon here on our 5 carbon chain, 1, 2, 3, 4, 5. And so we have 1 methoxy and then pentane, 1 methoxy pentane. Now, in terms of reactivity of ethers, I'll level with you. There's not a whole lot you can do with ethers. Okay, chemically, ethers are moderately inert. They normally don't react with the regular old reducing agents and bases. To be honest with you, most ethers are commonly used as solvents, okay, to actually dissolve your reactants for your reaction. However, let me also add to that another reason that you want to steer away from ethers is that they're really flammable. Okay, so they're pretty dangerous to work with too. You want to be careful around the ethers. Anyhow, that doesn't mean that we can't use ethers at all for reactions. There are reactions where we use ethers as starting materials, but I want to show you right now how to make an ether. Right? How would I make an ether? And probably the simplest way to make an ether is to take 2 alcohols, put them together. Okay, you'd stir these 2 together in some kind of flask. You add an acid catalyst. Remember, when you have H+, this is an acid catalyst. Okay, you heat it up, and then you form an ether plus water. The heat is key, right? Heat causes the loss of water. That's what I mean by minus H2O. Where's the water going to come from? We need a hydrogen and an oxygen and another hydrogen. And that, my friends, is where the water is going to come from. Look at what's left over. You're left over with 1 R group and an R group and an oxygen. And that's where your ether comes from. So that is how you would make an ether. And in fact, it's a very simple way to make an ether. Maybe not the only way to make an ether, and there's many other ways to make ethers, but this is certainly a reasonable way to make an ether. The key here, and I'm repeating myself, the key is heat. You need to have heat to drive off the water, and you also need an acid catalyst. So if you just say, okay, Mr. Dion, I'm going to take 2 alcohols and stir them together and make an ether. No, it doesn't work that way. You've got to have the right tools to make it happen. So you need to have that acid catalyst, and you've got to warm it up. You've got to heat it. What about other uses of ethers? Well, the ethers that are, again, normally used as solvents in the organic chemistry lab are things like diethyl ether. So we looked at that, right? This would be diethyl ether, very commonly used. Another one is called methyl tert butyl ether. That would be this. So we have a tert butyl group on one side and we have a methyl on the other. Again, these are widely used as solvents. But there are other uses for ethers. And in fact, ethers are often used as anesthetics. So if you've ever been anesthetized before, you might have been exposed to some ethers. You've probably even heard of ethers or diethyl ether being used as an anesthetic because it was used as an anesthetic a long time ago, like over 100 years ago. You can see what the problems would be. First of all, diethyl ether is highly flammable, so that's not good. Also, it had nasty side effects. So people would get very sick after they used diethyl ether as an anesthetic. So what chemists have done is they have designed several new ethers that are halogenated. What do you mean by halogenated? They have halogens attached to them. You see that we have all these different fluorines, right? What are the halogens? Fluorine, chlorine, bromine, and iodine. And you see that all of these have either fluorines or chlorines or mixtures of them. And the reason why we put all those halogens on there is several-fold. First of all, they're less flammable, so they're much safer to work with. And also, they don't have the nasty side effects that simple ethers like diethyl ether do. So we've steered away from diethyl ether since, the Civil War ended a long time ago. And we use much more modern ethers now. All right, let's move on to thiols. If you remember talking about alcohols with me, we talked about alcohols a lot in this class. We have an R, and then we have a hydroxyl like this. This is an alcohol. Again, we've looked at those in detail in this chapter. If you replace the oxygen with a sulfur like this, then you have a thiol. So a thiol is nothing more than the sulfur version of an alcohol. However, they're pretty different from each other, and there's some good reasons for that. Not only is there a difference in electronegativity between oxygen and sulfur, there's also a big difference in size between oxygen and sulfur. Could anybody tell me which one would be larger? Would oxygen or sulfur be larger? Which one would be larger, oxygen or sulfur? And I've drawn a little bit of the periodic table up here to help you. Yeah, sulfur is larger, right? Because we know that as we go down a group, atomic size increases. So size increases like that, okay? So again, similar in structure to alcohols with the sulfur replacing oxygen, but we're going to talk about nomenclature of thiols a little bit. The name is based on the longest chain with the suffix thiol, position indicated by the number. Now, if you're a little bit unclear about what that means, I'll clear it up for you. Before we go on, I just want to tell you something that's kind of interesting about thiols, is that thiols have terrible odors. Okay, so we could even add it in here. Terrible odors. They do not smell good. And that's why you'll never work with a thiol in an undergraduate lab. They smell so bad that everybody would, drop out of the class if we had to work with thiols. Here are some simple examples of thiols, and you can see that this is really the only slide I have because this is just some molecules that come straight out of our textbook. But if you look at the first one, this one here, it says it's called ethane thiol, right? Because if you have CH3 like that, that's an alkane, that's ethane. If you remove one of these hydrogens and you replace it with the SH, you end up with a thiol. So we call that ethane thiol. We don't have to call that one ethane thiol because it wouldn't matter if the thiol was on either side, it would still be on the first carbon because there's only two carbons. So it's kind of a simple example. Let's go down below it, okay, and look at this example right here. Same rules that we always follow. We find the longest carbon chain. It's highlighted in yellow. Here's our functional group. We want to give the functional group, the thiol, the lowest possible number, just like we did when we were naming alcohol. So we have 1, 2, 3, 4. We have a methyl group at the third carbon. So that's a 3-methyl. And so this becomes 3-methyl, 1-butane thiol. Okay? 1-butane thiol. And you might be asking, what about 2-butane thiol? Is there such a thing? Look, if I had 1, 2, 3, 4 carbons, and I had a thiol here, I would call that 1, 2, 3, 4. I would call that 2-butane thiol. Okay? There we go. Dithiols. I have 2 examples of dithiols. Again, these come straight out of the textbook. The first one is if we have ethane as our parent, right? 2 carbons, very simple. But we have a thiol, the SH group, on both of the carbons, 1 on each. Well, it wouldn't matter if you numbered it this way, 1, 2, or if you number it this way, 1, 2, because there's symmetry down the middle of the molecule. This becomes 1,2-ethane dithiol. So it's a dithiol. Same rationale for this big one down here. We find the longest carbon chain. We number it so that we give the lowest possible number to the first SH group. If we started here, we'd have 1, 2. But if we start on this carbon over here, we have 1, right? We have the thiol. And since 1 is lower than 2, we're going to start numbering here. We have 1, 2, 3, 4, 5. So this is 1,4-pentane dithiol. All right. If you feel like you need a little more practice in naming thiols, I've assigned some problems from our textbook that go over thiol nomenclature. A little more about thiols and scent. As I told you that thiols have terrible odors. Here it says they're nauseating aromas. Okay. For example, If you don't like the smell of onions and garlic, well, the strong odors that come from onions and garlic are not offensive to most people. Okay, they're good food, but a lot of people will get discomfort or feel like they might get a stomach ache or something if they eat too much onions or too many onions, and that's because of the sulfur in there. It can cause sort of an unpleasant feeling. Also, if you've ever smelled a skunk, the odor from a skunk comes from thiols. So here we have a picture. It's a weird picture, but it's a picture of a skunk with some roses. So two very different, some very contrasting odors here, right? If we look at the molecules on the top, they are found in the skunk spray. And you notice that both of them have thiols, right? Here we have a thiol and here we have a thiol. So nasty compounds, nasty smelling compounds, I should say, found in the skunk spray. However, in the geraniums, the roses, anyhow, the roses, you can see that we have alcohols, right? We have an alcohol here and an alcohol here. So good smell. So we'll say good odor, right? And then on the top, we'll say offensive odor, offensive odor. Anyhow, something to think about there. Let's talk about formation of a disulfide. And if you're wondering, wow, this looks pretty complicated, the reason that we introduced the concept of disulfide formation is, first of all, it introduces a new functional group. And second of all, it gets us to think about our oxidation reduction. And third, we're going to see disulfide formation in the chapters that deal with proteins. Later on, we're going to spend quite a bit of time talking about proteins and enzymes. First, let me tell you what a disulfide is. It's a brand new functional group. You all know that when you have RSH, right? We just went over this. This is called a thiol. So that's a thiol. If you have R and then you have two sulfurs linked together and then another R group like that, that's called a disulfide. A disulfide. Now, what is disulfide formation? It's a very specific reaction. Let me show it to you. Follow along with me here. It says the thiol disulfide redox pair controls a critical factor in protein structure called a disulfide bridge. So what happens is we bring two cysteine molecules that we have here. Cysteine, notice that there's an extra E in here, is an amino acid. So this is one of the 20 amino acids that are naturally occurring. So this is an amino acid, and these are identical, the two cysteines. What happens is they come together. You see here we have a thiol in the first molecule of cysteine, and then we have another thiol here. Well, what's oxidation in organic chemistry? It's the gain of oxygen or the loss of hydrogen. When we form a disulfide bridge, so we form a bond between the two sulfurs, we end up losing those two hydrogens that are highlighted in pink. Okay? We lose those, and we also happen to lose two electrons. Oxidation is losing. Think about it. OIL, oil is oxidation is losing electrons. So you can clearly see why when we go from the two cysteine molecules to the cysteine, or cysteine, which is what some people call it, cysteine and cysteine. Anyhow, that's an oxidation. If we go in reverse, if we go in this direction, the reduction, we can tell that when we go from the disulfide to the two thiols, that's most definitely a reduction because we're gaining hydrogen, right? We're gaining these two hydrogens in that direction. If you want to think about it in terms of reduction is gaining electrons, well, you can see that we're gaining two electrons too when we go from the cysteine or the cysteine to the cysteine, the two cysteines. Anyhow, this disulfide bond is important, again, not only in enzyme structure, but in protein structure. It also, if you have curly hair, it's responsible for, curly hair. If you get a perm, the disulfide bridge is responsible for, the perm. Anyhow, I'm not going to ask you anything about the disulfide bond found in insulin or the structure of insulin. We'll look at that later on. Next, we just have a little summary here. Some reactions of alcohols. You need to know about the hydration of alkenes. You need to know about the Markov-Nikov rule. So Markov, Nikov, that's not going away. The reduction of an aldehyde or a ketone. we said that an aldehyde gets reduced to produce a primary alcohol. We said that a ketone gets reduced to form a secondary alcohol, and we looked at the conditions for that. Then we talked about the dehydration of alcohol, so that means you need to know Zaitsev's rule. Zaitsev's rule. Okay, we talked about oxidation, how a primary alcohol is oxidized to an aldehyde, and then it can be oxidized again to a carboxylic acid. It's not on here, but it's important. How you can oxidize a secondary alcohol to a ketone, and a tertiary alcohol doesn't work or doesn't react. We talked about the dehydration synthesis of an ether, right, where you take two alcohols, say R prime, R double prime, like this. We treat them with an acid catalyst. We heat them up. We end up with our ether and water driven off. So that's another reaction you need to know from this chapter. And here they all are summarized right here. Okay. The only thing about this one is the dehydration reaction doesn't exemplify Zaitsev's rule, but hey, it's on there. All right, and then I have a list of practice problems from the book that I would recommend that you look at.